Hello, everybody. This is Fundamental Review 1 for the turbocharger subsystem on our Cal Poly's Formula SAE car. So the purpose. What is the purpose of our subsystem? The purpose is to push the boundaries of our current internal combustion engine. We have been pretty stationary in terms of our limits and the things we've been doing for the last couple of years. We've considered changing over to a single cylinder unit. We've considered changing over to like the Triumph 3 cylinders, but and we've done a couple of other modifications to our engine, but nothing has really given any sort of great advancements in the terms of like our power output. How does it function? And I'm pretty sure most of you guys know how it functions, but if you are stuck under a rock and don't know, the basic principles is that there's as the exhaust gases come out of the engine, they go and they spin a turbine. The turbine is connected to a compressor with the shaft. And the compressor, as the name suggests, compresses air and puts it through. You can have an intercooler or not. And the compressed air then goes to the engine, giving you a more dense air for you to add more fuel into, and in turn making more power. Turbochargers have been around since the same time as internal combustion engines have been around. They primarily came into effect around World War II, when bombers and fighters wanted to go to higher altitudes and outrun to competitors. So turbochargers are what made it possible, because the farther up you travel, the air is less dense. So you need something to compress it to be able to produce the same power that you were making on at atmospheric pressure at sea level. So how does it interact with the other subsystems around it? So the primary contact is the entire powertrain system. Everything's gonna work together. Of course, it's gonna be, the exhaust gases coming out of the engine is gonna be bolted directly to the exhaust, and it's gonna be bolted directly to the intake. Now the intake is gonna kind of change its role, because it's gonna go from making sure to contain vacuum. Now it's supposed to contain boost. So the design of the intake might change a little bit, and it might need to be made like a little bit thicker, a little bit stronger. The seals have to be stronger, and those things have to come into account. Like you can blow an injector seal and things like that. Fuel, more power, more fuel. Might need a bigger fuel tank. I'm sure the stock injectors can handle the power limits that we're in, and tuning to make sure everything is sane and sound. And secondary contact, I think everything else is a secondary contact, because as our powertrain makes more power, every other subsystem has to compensate for that. The brakes have to be bigger. The car is going to be more on the limit, so all the other subsystems have to be ready to perform perfectly at the limit. So this is a cutaway of a turbocharger. There you go. In the center, we have the center housing assembly, where you have ball bearings or journal bearings. Now in this turbocharger, it has cooling ports. So it takes the coolant from the engine and recirculates it through the center. Now some turbochargers have this, some don't. But the one thing that they all have is a oiling system. So this is the oil gallery right here in red. They all have a oiling system, and that's the primary cooling for most turbochargers. On the right here, we have the hot side, the turbine wheel. Now most turbine wheels, you have this is a variable, let me walk this out here. This is a variable vane turbocharger. So, and then this is the compressor side. And as you can see, they're connected through a shaft. This is actually the actual name of the compressor wheel is an axial centrifugal compressor. Kind of a fancy name, but yeah, kind of the basics. Pretty cool thing. Everybody loves turbos. So show a picture of the subsystem. Now, I have found it extremely difficult to find a exact CAD model, SolidWorks model of the turbocharger that I am kind of thinking about, or the two that I'm kind of thinking about. But those, I don't know, for some reason those are not online. So you have to contact Garrett specifically for the sponsorship and also for the models. But this is the only one I found, and I just want to show you guys where it would sit on the card. This is the 19 chassis, so the current rolling chassis that we have. It's going to be on the left side. As you can see, the exhaust manifold comes out here. It would travel up to about the driver's shoulder line level, a little bit lower, and then the intake would run. The compressor side would run back into the intake manifold. So kind of like that. This is a huge turbo, so it's going to be a lot smaller in actual size. So like in 2019 at Lincoln, I grabbed some pictures of the Michigan car. These are kind of crappy pictures, but I think they'll do just to show how other teams do it. Michigan's thing was pretty cool when I remember the first year that they ran a turbocharger, but reading back on their things, they said that they implemented it within 12 days. So from the first day that they decided to do a turbocharger, it took them 12 days to have a running car. I think that's pretty cool, right? And if you can see right there, on the left side, they're running their turbo. I mean, I know technically on the right side, but here on the left side, they're actually running a Ford Focus turbocharger. Ford Focus turbocharger. You can see the turbocharger right there. That's the wastegate. That's the oil line, and that's the air coming out. And on the left here, you can see they're using the exact same throttle body that we're using, the Bosch unit. And right here, you can see the blow-off valve. It's a pretty simple system. You can see their intake, a carbon intake. I think they have changed it a little bit since then. I think they're currently running an intercooler as of 2021, but back then they were not running an intercooler. They were around, I don't remember the exact number, but it was between 6 and 8 PSI. So yeah, I think that's pretty cool to see at other schools, because in most pictures that schools post, it's very difficult to see like close-up exact pictures of their specific subsystem. So going into the theoretical, now with naturally, we've been naturally aspirated, of course, and we're looking into forced inductions. Now this change is kind of, it's a little bit more difficult than just going if you were not restricted. So the fact that we're restricted kind of changes the math a little bit and kind of makes it a little bit more difficult to come to an exact conclusion to what specific turbocharger you need. For example, this is a turbo map on the right here, and I'll get into that in a little bit. And this is the actual turbocharger that I kind of have in mind. It's the Garrett GT06. It's actually one of their sponsored turbochargers that they sponsor SAE teams with. It's just the one that kind of like the calculations kind of add up to this one a little bit. Other theoretical. So there's 4 main kind of components in a turbocharged systems. You have the turbocharger, you have the intercooler, a wastegate, and a blow-off valve. Now, wastegate is about 90% of the time you have it built in with the turbocharger. So it will open up a port inside the hot side of the exhaust when it sees a certain pressure inside the compressor side. A blow-off valve is a little valve on the compressor side, which will let off excess air when you shut the throttle body off, so it doesn't surge the turbocharger. And we're saying surge, that means there's too much buildup on the left side of the compressor map, and that turbulence inside the turbocharger can cause vibrations, will basically cause the turbocharger to explode. And we have an intercooler. For us, it's a little optional because depending on what PSI we run at, and depending even what state we run the competition at, it can have a great impact if we are going to need an intercooler or not. So let's get into the theoretical numbers here. So it's going to go from the left to the right. So we are looking at a Yamaha R6 engine with a bore of 67 millimeters by 42.5 millimeters. Now, this calculations right here is for a turbocharger, is going to be for the turbocharger selection. And how you select a turbocharger is, again, by looking at this map right here. So if you can see, on the left, we have the pressure ratio. And on the right, we have the corrected, right? That's important, corrected airflow. And these islands are the efficiency islands that you want to be in, right? So the GT06 is a, it's this actually the map of this turbocharger. It's rated for like between 60 and 100 horsepower. So kind of in our little area. Okay, so back to this. Now over here we're calculating the displacement of the engine. So how much what's the total displacement per 2 cycles of the 4-stroke of the revolutions? Yeah. So when we do the math, we get 36.6 cubic inches of displacement, right? Now from then on out, we can calculate our volumetric flow rate in cubic feet per minute. Now this is calculated at the RPM is 11,500, right? So I've selected that kind of as the red line in a little bit, because after that we kind of lose power. So I've chosen that as the peak. We rev out to 12,000, I think, but I think at 11.5 the map always drops off, so I've selected that. But this is going to be put into an Excel model just so we can get an exact map of at what RPM the turbocharger is going to be where. So just know that that's a variable, of course. The 3456 is a constant, and we get a number of 121.78 cubic feet per minute. Now this is the exact output, the output of the engine at 100% volumetric efficiency. And no engine is 100% volumetric efficiency. In fact, from like online or just from credible sources, okay, they have stated that the R6 engine is a very efficient engine, being at 0.88 volumetric efficiency, right? And that's not restricted. Individual throttle bodies, like full stock setting, 91 octane gas. In that state, the engine produces 117 horsepower, incredible amount for such a tiny engine. But now we need to calculate the actual cubic feet per minute output of our engine, right? So our engine has a 20 millimeter restrictor, meaning so it can in no way be as close to stock, obviously. And from our dynographs of a couple of years ago and just other schools that are using the same engine around the stock configuration, everybody's around 68 to 75 horsepower. Now I've chosen like 70 horsepower just to kind of be in the same ballpark and just to be fair, and just, it's better to be low. So from then on, from 70 horsepower, now comparing that when we do the calculations versus 117 at 0.88 volumetric efficiency compared to stock, our restricted volumetric efficiency is about 53%, right? And from then on, the actual cubic feet per minute output of our engine is 64.54. This is the corrected one for the restricted. Excuse me. Now from here on out, we move over to the pressure ratio. Now the pressure ratio is basically the ratio of the boost you're going to produce versus kind of like ambient. Okay, so that's why we're dividing by 14.7. So that's at sea level. Now on the left, right here, on the left, right here, the 7 number is the boost goal, right? Now, the reason why I've selected 7 is just wanting to be on the lower end. It's like, let's start out with this and see how the whole system is working. And from then on out, we can work up, right? We don't want anything to get too hot, or it's like we want it to be simple, safe, and a lot of like, stock cars are around this number. A lot of like tuned stock configuration cars are around this number also. So it's just a safe number. 6, 7, 8 is a safe number to be around. Now, plus 14.7, that's atmospheric pressure, and subtracting, excuse me, the -1 is the, for example, that is the losses, the pressure losses through your system. So for example, an air filter accounts for example, 1 PSI. An intercooler accounts for another PSI, right? The long piping in stock cars that they have, that accounts for another PSI, right? Or it could count. So like in a stock car, when you're turbocharging it, you get about 2 to 3 pounds of loss through the system once it reaches the combustion chamber. Now for us, if we choose not to run an intercooler, if we have no air filter and we have like pipes this long, I don't think we're gonna have much losses. So I wrote 1, right? And that gives a pressure ratio of 1.4. So we're gonna compress the from atmospheric to like 1.4 times. From here on out, we can do the calculations for the temperature at the outlet of the compressor, right? We do the math, and now this math also it includes the pressure ratio, so it's very dependent on the pressure you want to be at, so 7 psi. From here we can see that our temperature at the compressor is 158 degrees. So as you raise the pressure, that number is going to go up. And this number is also very dependent on ambient temperature. So as you can see here, I've chosen ambient temperature to be at 85 degrees. And at the bottom here is a turbocharger efficiency, so 75% efficiency. That's again a very, it's not a guess, but it's just like a perfect scenario in a way. And even 85 degrees is a perfect scenario, because if we look at Las Vegas, the competition there, their ambient temperature was 115 degrees and was that like a month ago or something. So if we're running like 8 psi boost at 115 degree ambient temperature, our compressor output temperature is going to be at like 200 degrees, and we're basically going to be boiling off the fuel. So not very good. From here, wait, let's move myself so I can go to the right. Again, these numbers are just good numbers to look at and help us select the turbocharger. So on the right here, we're kind of reaching the end of this part. So from here, we can calculate the mass flow rate of the engine, right? As you can remember in the previous slide with the turbo map, we're looking at the mass flow rate. Now, this is the mass flow rate that we're calculating of the naturally aspirated engine. So atmospheric pressure, the 2.7, I think is a constant. And then 64.54 is the CFM of our engine. And then from there, we get 4.7 pounds per minute of mass flow rate. From there, we can, well, not from there, but like we calculate the density ratio, and the density ratio is kind of like the pressure ratio, but dependent on temperature, right? So because temperature has a lot to do with the pressure of the air, I mean the density of the air, sorry. So 1.4 times like, ambient divided by the temperature at the compressor outlet, we get about 1.23 density ratio. Now this is at 7 psi. So air is compressed 1.23 times more than atmospheric at 7 psi and at 85 degrees ambient temperature, right? Now, if we take those two and subtract to each other, we can get the corrected airflow, right, to be at 5.78 pounds per minute, and our pressure ratio is 1.4. So we have found our pressure ratio and our and we have our corrected airflow. The corrected airflow is basically the density ratio multiplied by the mass flow rate. So we have, and those are the two numbers that we need for here to select the correct turbochargers. Now, so when you would do this, is like I would put this into, I would put all of these calculations into an Excel, right? And type in the specific RPM and the different variables and make a line right here as it goes through the turbo maps. We do not want to be on the left side and we do not want to be on the right side. So on the left side is basically when the butterfly valve is closed, but the turbocharger is still making boost. So it just slams into the butterfly valve and comes back and basically surges and overboosts the turbocharger itself. This can have a lot of damage on the physical properties of the turbocharger itself, because the vibrations is not good, and it can basically shake the entire thing apart. You don't want to be on the right side, because on the right side, the butterfly valve is all the way open and it's spinning all the way. The turbocharger is spinning at max RPM and it's basically stalling. So again, not good. That's that. That's the math. Oh, but so then we can use those numbers to kind of land in the pressure ratio chart. Now, as you can see here, there's a lot of many variables. So that's why it's important to talk to an actual Garrett person too, just to like talk to them and show her these numbers and be like, how accurate is this, or how accurate is it to follow this idea? I don't know. So historical accords, there are no historical accords that I know of, but we can look at other schools for inspiration. Stuttgart runs it, Michigan runs it, and I think there's another school I forgot to mention that runs it. So goals. Yep, right, back. Yep, how do I play this? That's the goal. All right. Let's go back. So yeah, goals is more power. Okay, so and then more goals. So successful completion of the entire subsystem, I believe I don't think it's that hard. If anything, what I think is actually hard is getting the actual math right and having the validation done. We want reliable and consistent performance. I don't want keep overboosting the intake and then keep cracking intakes. I don't want breaking, exhaust manifolds and cracking, those components. I don't want accidentally overboosting the entire thing, and then and I want it to be very tunable and controllable so that our tuner can be able to manage the entire thing. That's why it's like I only want to be at 7 psi. That's why I don't want to be any higher, because then these things can it's we need to do like small increments and try and see how far we can go up. Goals, achieving goals, how to obtain this goal through fundamentals and design. First of all, I need to contact Garrett for a sponsorship and get the actual models for the turbocharger and talk to them about which turbocharger we need. And also for achieving goals, there's a couple of components that, depending what turbocharger we have, we might need to again do some Inconel 3D printed components just to have like a perfect, beautiful looking piece, so we don't have to do some crappy weld jobs. So I think that'll be pretty cool to contact them and contact other people for like maybe a sponsorship for blow-off valves. I mean, obviously Garrett for the turbocharger, and the intakes can have to be changed like a tiny bit. So just reprint a new intake, plenum, right? So it's going to be a side suction intake, I want to say it. So the cylinder is going to be blocked off, and then it's just going to take it from the side. So yeah, so just contact the sponsor again. Just be like, hey, can you make me a new intake super quick? Future plans from now to fundamentals 2. So again, like validating the turbocharger calculations selection with my numbers, making the Excel sheet, and also Garrett helping out a lot in validating these numbers, giving me better numbers. I would like to have a sort of a complete model, just so I can make everybody happy and just start building the shop. And starting the senior project proposal, just because this is my senior project. So proposal for the administrators, I mean, not my advisor, I guess, whoever that is. So start the paper for the advisor and all that. So there you go. Thank you. Oh, wait, this. All right, thank you guys. And then I guess when you have questions, I guess we're going to be in a meeting now. So ask your questions.